Previously, we used universal modus tollens to fill in valid conclusions for the arguments. When we do this, we use the rule of universal instantiation, which means if a property is true for everything, then it should be true for a particular thing. So we're going to combine the universal instantiation and the universal modus tollens to fill in valid conclusions for this argument. So we have a conditional statement. If a number is even, then its square is even. A number here means it's any it could be any number. Of course, because of the condition hypothesis, this number has to be an even number. So pretty much this is for any even integer, the square of this even integer is going to be even. So if this property works for any even integer, then it should work for a specific even integer. So if we 2 is an even integer, then 2 squared should be even, which is true because 2 squared is 4 and 4 is even. Well, we haven't proved this property here, but this actually can be. This is a property for, in number theory, which can be proved later. But right now, we're just assuming this property is true, and we're going to use this to fill in conclusions. So here, if we know k squared is odd, so k squared represents a specific odd integer. What conclusion can we get based on this property? Well, this is the the condition that a squared is odd, and that's negating the conclusion. And we know if the negation of the conclusion is true, and then the negation of the hypothesis is true, which is the contrapositive. And we know the contrapositive and the original statement are logically equivalent. So if we know if a k squared is odd, which means k squared is not even, so that's the negation of the consequence. Therefore, we should know k is odd. K is not even. So pretty much it's like doing contrapositive. If we have a conditional statement like this, if a number is even, then its square is even. If we think about a contrapositive statement, it's saying if the square of a number is even, if the square of a number is not even, so we negate the conclusion, then this number is not even. And we know not even pretty much means it's odd, because any integer is either even or odd. So this means odd, and this also means odd. So it's like saying, the contrapositive is saying if the square of a number is odd, then this number is odd. And because k squared is odd, so it's a special case, because this number could be any, the square of a number could be the square of any number, and k, so we plug k for this number, and the square of a number would be k squared. So if k squared is odd, then of course we get the conclusion that this number k is going to be odd. So over here we're still using universal instantiation. Again, the rule is if it's true for any number, then it's true for a specific number k. Okay, so this argument here is called modus tollens. It's sort of like using the contrapositive.